So now we're going to take a look at the material in section 3.7, and this section is all about something called optimization and using calculus in order to optimize certain things. So an example of this is given in example 1, but let's kind of go through the basic outline of our thought process on these kind of problems. First off, we want to make sure we understand what are the unknowns, what are the quantities which are given, what are the conditions that these things are given under. Most of the time we're going to draw some sort of picture or a diagram to help us take the quantities and the unknowns and give us something to look at to help us put them together. We also want to introduce notations, letters and symbols so that we know what each of these quantities are, and we can talk about their formulas and all that kind of stuff too. We're also going to be dealing with the derivatives as well, since the derivatives can tell us about maximums and minimums specifically. So I'm going to show you all an example here that illustrates the optimizations that we're going to be using our calculus for. It says a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders on a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? So looking at this, we can see what we're trying to optimize is the area contained within the fencing, the square footage, with 2,400 feet of fencing to use at our disposal. So let's start out by kind of drawing a picture of the situation here. This will be our river, and then we have maybe sort of a rectangular shape of fencing along here. Let's go ahead and make this A stand for area, W will stand for the width, and L will stand for the length. And so we know that the area will be length times width, and that's what we're trying to optimize. And beyond that, we can also talk about the perimeter. The perimeter is 2W plus L. Since I have two lengths for the width, but just one for the length because we're not fencing along the river. Now it tells us the 2,400 feet, that's going to be the total amount of fencing we have. That's the total perimeter, no matter how we configure it. So 2,400 is equal to 2W plus L. But what we're trying to do is optimize area. So in order to take that area, length times width, and use it for optimization, we need to work it down into just one variable from the two that we have. We can do that by using the perimeter of 2,400 equals 2W plus L if we solve it for one of the two variables, and then substitute that in for the area. So here's what I'm going to do. I'm going to solve for L. So take the 2,400 equals 2W plus L. L is going to equal to 2,400 minus 2W. And now what we're going to do is we're going to substitute that into area equals length times width. So that's going to look like A is equal to 2,400 minus 2W times W. Or simply A is equal to 2,400 W minus 2W squared. So now with this information we're going to find the absolute maximum of area. And so the way we did this in earlier sections is what we did was we figured out the first derivative, the critical numbers, and used those to determine the absolute max and absolute min. However, one thing we do need to figure out is what's the biggest and smallest that the length and the width can be. what's the biggest and the smallest width? Because we want to know how big and how small this can get, basically. So the smallest would be, could be 0, because that would be no width to it. The largest, however, is if we split the 2400 evenly between the two sides for width. So that would be 1200 for W. Two lengths of 1200 would be the 2400 total fencing that we have. So that's the smallest and the biggest we can make, the width. Now what we're going to do is we're going to find the critical numbers from the area up above. So to do that, we find the first derivative, a prime, which is going to be 2400 minus 4w. Now again, we have to set this to 0 to solve for w. And so see here, we have 4w is equal to 2400. And when we divide out the 4, we'll get w is equal to 600. So what we have here is basically three numbers to check to see which one yields us the maximum amount of area. Which measurement for width would give us that maximum area. And so it becomes just a check of plugging the numbers in for w. So if we use w equal to 0, our formula up above for area went 2400 times w minus 2 w squared. But that's just going to be 0. No area whatsoever. For w equals 600, the area would be 2400 times 600 minus 2 times 600 squared. That comes out to be 720,000. So that is looking like it's probably going to be the largest, because if we plug in 1200 for w, which again is the largest width we can possibly produce, and plug that in and do the calculation, it looks fairly large here, but it actually comes out to just be equal to 0. So this right here, that tells us the maximum area we can possibly create is 720,000 square feet. And that happens with dimensions of 600 for width, 600 feet for width, and then for length, we can calculate the length by doing 2400 minus 2 times 600. That comes out to be 1200 feet. So 1200 by 600 dimensions give us the maximum area here.